This course on autonomous robotics is built around the idea of a mock grand challenge. Suppose that humans were to colonize Mars by first sending resources, then autonomous robots to prepare for humans to arrive later. How could one build and program a robot to manage this environment? Specifically, this challenge sees us tasked with locating and collecting sets of red, green, and blue blocks, and then setting them within a designated drop zone with limited input from a human operator. I am Ryan Bates, and I am a student who has completed this course. The basic construction of our robot includes 4 motorized wheels with magnetic encoders, a servo motor gripper, a Pi camera, and a sonar distance sensor, all driven by a Raspberry Pi 3B+. Other hardware elements have been added as needed. The Raspberry Pi is important as it's a full computer with a full Linux operating system. Important for us are the general purpose input and output pins, which we can use to control pulse width modulation of the motors, signals, and duty cycles for the servo grabber, and I2C serial connections for our B&O orientation sensor. We control the gripper by sending a duty cycle that corresponds with the desired position. I have also added cardboard extensions, as seen in the first video, underneath the claws to reduce the chances that a block will be knocked down and missed by the claw by accident. I have also added a protective pilot barrier in front of the robot, but behind the claw, to prevent other blocks from interfering with our wheels. Also on top, I've added an auxiliary battery supply so the robot can effectively charge and be used simultaneously. I've also added, there are 2 red boards on the back of the robot that are external H-bridges. One is an unused spare. These H-bridge boards are important because they allow us to change which circuit we are using for each set of wheels, left or right. That is, if we want to go forward on one side of the robot, we need to have the current flow in the opposite direction, as it would have going backwards, giving an H-shaped diagram of circuitry. The boards also allow us to separate the low amperage signals from the Pi with the higher power that the motors actually consume for movement from the AA battery packs. One of the trickiest sensor categories on the robot are those dealing with localization. One wheel on each side of the robot is fitted with a magnetic encoder and a paired Hall effect sensor. As the wheels turn, the magnetic disc spins, and the sensor can detect the changing magnetic field. Note that our encoder only has 8 poles, so its resolution is limited. Other alternatives that we did not use include optical encoders, which replace magnetic poles with visual stripes, possibly of higher resolution, or a quadrature encoder, which allows us to know which direction the wheel is turning. I stuck with the original magnetic encoders for tracking distance, but due to factors such as wheel slip, I explored alternatives for orientation instead of gauging the difference between encoder counts between the left and the right drivetrains. I bought and installed an MPU 6050 sensor from Amazon, which had gyroscope accelerometer readings to determine orientation. However, it does not integrate and synthesize the readings together itself, which would leave the Raspberry Pi to handle the real-time mathematical tracking for orientation, a difficult task to include with a live video feed of dynamic frames per second. I also tried using my Android phone as an auxiliary sensor. Androids commonly have gyroscopes and accelerometers as well, so I created an app that would make the phone's orientation, and therefore the robot's orientation, available on demand. The phone would handle the orientation calculations itself, however it proved to be inaccurate. A 90-degree turn in real life would not correspond with an approximately 90-degree different reading on the phone. This was also visible with other apps on the phone. Finally, I settled on a B&O 055 sensor, which is an absolute orientation sensor. This chip handles the fusion of readings into an orientation data on its own in a more accurate manner than the phone can do. Finally, we have the motors. 4 motors, 2 on each side of the robot, being controlled together. Distance and turning speed can be mathematically calculated via the gear ratio and physical dimensions of the robot, but one must take into account slippage, different surfaces, etc. I would manually empirically calibrate for each surface I used instead. The software is highly reliant on the Python implementation of OpenCV for image processing. The algorithm filters the camera feed for the hue saturation value mask of the desired block, or in this case traffic light, and identifies the contour with the largest radius that fits it within acceptable range of the image. The acceptable range is considered not too high, which would be above the floor, or not too low, which would be as part of the too low on either corner, which would be part of the claw, but in the sweet spot in the middle. We will look for the contour with the largest radius in the sweet spot, and we turn left and right until it is located horizontally in our center, then approach, readjusting if it goes off center. Once we are close enough that it is located horizontally in our sensor, then we can declare that it is close enough in our grasper that we can grab. Both the color filters and the speed and other settings are tweaked by location, so I can change a constant in my code to switch between settings calibrated for each location I've tested in, such as my house, a friend's house, or the Robotics Realization Lab. The software also utilizes SMTP for sending images remotely over email to report where it finds the different objects. I also use a dual state machine for tracking where we are in the larger algorithm. Not only can I alternate between manual control and alternate control, but within the automatic control, I have a major state that determines our larger task and a minor state that is indicating the subtask within that larger task. Now, note that I did not have live video from the robot saved during the run. I did this for higher performance purposes. However, here's a recreation where I am saving off the bird's eye view, the robot's view, and even the live mapping. This gives me excellent situational awareness of what's going on. Ultimately, in the end, I was able to successfully gather a blue and a green block, but struggled with the red filtering. Additional calibration could assist with getting the red filter in the future. More incidental challenges included blocks getting tangled in the wheels, where a better frame barrier might help with this, an oscillation of what the target is as well. That is, the robot would see a block on the left, turn towards it, then see a block on the right and turn towards it instead, switching between the targets, but always identifying the one off to the side as the true target in that moment. I could also add some weighted inertia to keep the focus on one of the targets in the future. I was ultimately able to mitigate some of these issues during the run by requesting resets using a tool I wrote to combine the maps at the end, producing an ultimate post-process map that combined the different elements from the ones before. Now, there were also some other issues that I had seen throughout this project. For example, sometimes the wheels would come off on both my robot and other people's robots. In these cases, we would have to make sure that the wheels are either checked before each run, or, as other people did, just glue them on in general. Also, as you can notice right now, there is a block that is stuck with the wheel in the robot. If I had extended the barrier around the robot, that might not happen, and therefore interfering with our operation. Other issues I saw is circuit integrity being destroyed when the battery pack holding the AA batteries was damaged. This made the batteries not sit very well in there, meaning that the circuit would break depending on how it was jostled. Finally, don't fry your Raspberry Pi. When it was on top of the robot, it either touched the metal frame or a metal screw at such an angle that I believe that two of the metal leads underneath short-circuited, frying the Pi ultimately. So I had to fix this with another Pi. Overall, there were a lot of obstacles here, but I believe I was successful in grabbing a number of blocks, and I have learned in the future that I really need to prioritize testing for testing's sake. This means that I have to try to get through a complete loop of testing as soon as possible, rather than focusing on just a specific element and fine-tuning that one element. Among other things, localization is extremely important because you can't even run a basic test with that overall. Thank you for watching my presentation.